Doing well, doing well. Hey, let's jump in here. Um, so I guess we'll start with check-in. Where are folks with regards to the course? Are you? I guess we can start with the couple of new folks. Have you been following along with the courses in this sequence thus far? You know, via the videos or remotely, or are you just getting started?
Right, Sam. So this is Shubhachish here. Can you hear me?
Yep, we can hear you.
Hi, Sam.
Hi.
So actually, this is something I got inside another Slack channel, probably in the Stanford CS224N. So I just joined in here. So I just wanted to know, what is this course about? I thought this is just a discussion forum. So is there any course behind it that we go through on regular basis?
Oh, so this course is the AI Enterprise Workflow sequence on Coursera. So this is the this is the 6th of 6 courses in this AI Enterprise Workflow sequence that is talking about, I know you can think of it as kind of advanced data science or data science in practice, however you want to think about it. But the focus is kind of reviewing the realities that data scientists face when they are working in large enterprises, and the kinds of things that you don't really learn about in some of the basics courses, but that become important when you're trying to do real world data science and get models into production. So the current course that we're working on or just getting started is AI in production, and we're starting to talk about topics like monitoring models, doing unit testing, things like that.
Okay. Okay, let me check out the course. Probably I'm actually starting on this pretty new. So let me go through the course. I'll be try to be regular in this meetup session so that I can catch up.
Cool. And then if you go to twimalai.com/AIEW, the playlist of the previous sessions is on that page.
Oh, that's great. That's good. I'll definitely check out.
Cool. How about you, Wen? You there? Tracy and Jose?
Yeah, up to the reading material on the security stuff. That's about as far as I got this week.
Got it.
And I got through all the reading material. Just didn't do the case study. But I did do all the unit tests and security stuff.
Okay. And have you the two of you caught up on the previous case study and code and stuff, or did you just do the readings and kind of move on?
Still
on
my to-do list.
Okay.
And
I haven't given up, but I haven't done it either.
Jose?
Yeah, I've caught up through all the code through course 4. Course 5 is on my to-do list, but hopefully this coming week.
Cool. Well, we'll talk a little bit about this one. The case study for this one is kicking my butt. Just a lot of this one, and I ran into a little bit of this last time or the time before, I think I mentioned, with when I was messing around with Kubernetes, but it ends up being, and I think this is in part the point of this course, not really any of the kind of machine learning specific stuff, but stupid things like module import paths for Python, and that kind of dealing with Docker build files or Docker files and just stuff like that ends up taking things that should be conceptually very simple and that made a lot of sense when kind of reviewing the material, take a lot longer than one would hope. But we'll talk a little bit about that as we dig into the projects and case study. So this is, again, the first week of course 6, we're focused on feedback loops and monitoring. Coming to the end of the sequence, we spoke last time about project stuff, and I guess we'll talk about that a little bit at the end as well. But just digging into the specifics of this week's material, the learning objectives this time are to discuss the different feedback loops that we run into in the AI workflow, to discuss unit testing and how that comes into play in model production, to talk about monitoring, different processes for monitoring the performance of models in production, as well as performance drift, and to describe some general principles for understanding models in business contexts. I'm not really sure actually what that last one corresponds to in the context of the course material. Perhaps it's the conversation around feedback loops, which is where we'll start. So this is a nice picture that they include in the discussion of feedback loops. The main idea here is that the data science workflow is highly iterative, and by iterative, that means that it consists of loops of loops. And at any point in the process, or at multiple points in the process, you might want to or need to return to prior steps in order to get the results that you're looking for. And so some of the interesting places that they called out where feedback loops are worth keeping in mind, like we know that in the, in EDA, the EDA is a feedback loop. EDA being exploratory data analysis, you're kind of, you do a visualization, you see if it tells you it's something interesting, you do another one or change the one that you did. We know that's a feedback loop. We know that feature engineering is a feedback loop, where we're modeling, where we're, creating features and training models and see if they give us the performance we're looking for. But these are some interesting feedback loops that relate to when models are in production and we might want to go back to earlier points in the process. So the first one is, if we have a model in production and, we should be looking at the extent to which the model is producing the kind of business impact that we hoped it would have. If we put a recommendation model in place and we want that to increase our sales, we should be looking at whether that's actually happening. And if it's not actually happening, we should go back to kind of the very beginning of the process where we're talking about the business opportunity and start to ask some questions about, do we think that the, this path of recommendations, will lead us to the business objective that we're looking for? If so, yes. If why not? And what's the opportunity cost of continuing to go down that path? Likewise, we'll often see a feedback loop from production to data collection. This is particularly true in deep learning, where you've collected a lot of data and you aren't achieving the performance that you need to see. Often, quote unquote, simple solution is to collect more data. It's simple, but not necessarily cheap or easy, because in order to use that in training, your data needs to be labeled. Another feedback loop they mention is production to exploratory data analysis. And this is relating to what I was discussing earlier. Once the model's been in production for a while, we should be looking at the relationship between the model's performance and the business metric that we're trying to impact. And finally, production to model selection and development. If we're starting to see poor performance in production due to performance drift, or if we get our model into production and it just does not perform to our requirements due to, for example, latency issues, it may be that the type of model that we're using isn't appropriate for our use case. An example that they gave in the material is if we're trying to do inference and we have a latency window of X due to the kind of user experience we're trying to provide, and maybe we use a Spark, we deployed the model via Spark. Those tend to have longer latencies than deploying the model via scikit-learn. So maybe that's something that we can try. So these are feedback loops that we encounter late in the machine learning workflow. Any questions on this stuff?
And maybe you're going to talk about this more, but it seemed to me like one of the sources of drift was more for like recommender systems, or one-shot learning systems, which are constantly changing with respect to the input coming in. Would that be kind of a fair observation?
And we're going to talk about drift in a little bit. This conversation here is at a little bit of a meta level. If you see drift, what do you do? Well, if it's really bad, maybe you start to question your life and go back to the business opportunity. Should you, really be working on this? If it's, less significant, maybe you just need a different model, or maybe you need more data. Those are the kinds of issues that I think they're trying to highlight here in talking about these feedback loops. So next we're going to talk about unit tests, and then after that we talk about performance drift. So unit testing for machine learning models. So unit tests are fairly common in traditional software engineering. The idea is, and actually there was a discussion that I guess I did not pull into here that was talking about the different types of tests that you tend to see in software engineering. One of the most common tests is called a unit test, and that's where you're trying to test small, isolated units of code, and you're often you're trying to test very simple things or small things about their behavior and whether they're behaving in the way that you might expect. And so in the example, in the case study, we'll see building unit tests to, around our logging infrastructure. When we call a log function, is it, creating a log file? Is it appending to the log file? Is the information that we called the logging function with resulting in a line in the log file? If we're calling a model predict function, can we give the predict function, unexpected format, data in an unexpected format and it not blow up? Like, can we send it a NaN? Or if it's expecting a number, can we send it a string representation of the number? Those are the kinds of things that you might test with unit tests. And unit tests are different from, unit tests are a kind of a way of implementing regression tests. Regression tests just being a way, the idea of using testing to see if things break, put simply. And that's in contrast to like integration tests, which are using testing to see if the various pieces of your system work well together, as opposed to in isolation, which is really what unit tests are doing. And so these tests are small and isolated. They typically result in a true or false. They're kind of pass-fail tests. They in traditional software development, there's this concept of test coverage, where, you know, in some environments, some, you know, businesses, test coverage is something that is measured, and this is true in open source projects as well. And you want to achieve as much test coverage as possible. The course makes a the course makes a good point about while unit testing can be very helpful in the context of machine learning and can help avoid errors or bugs that you know run into later and that you find and don't expect. There is a bit of a trade-off in that a unit test kind of puts a stake in the ground and says, this is what I expect to see from you know, my model or my system. And that can be at odds a bit with experimentation, which is a big part of the machine learning workflow. And so unit tests are typically something that you're going to want to start to use later in the workflow process. And, you know, in this course sequence, we're starting to look at them when we talk about production, as opposed to, you know, building unit tests early in the modeling cycle. They also made this point that that I'm not sure that I agree with. Unit tests also help ensure that when software fails, it fails gracefully. This means it stops execution without causing additional errors and takes steps such as closing open connections or saving data to a file that may be necessary for recovery, ... They kind of, I think in making the statement, they gloss over the idea of like test time versus runtime errors. You could use unit tests to help you ensure that when software fails, it fails gracefully by testing the, you know, the things that you, the graceful failures that you anticipate, like if you blow up, you know, do you close connections? Or if you blow up, do you save recovery data to a file? And it also helps you avoid blowing up by, you know, allowing you to test the corner cases that you can anticipate that might cause you to blow up. But it doesn't necessarily, it's not like magic pixie dust or a library that you can, you know, add into your code that will, you know, a blow up happens and it will in the background kind of close all connections and stuff like that. The module mentions some unit testing libraries. We mostly work with, in the case study, the built-in unit test library, but there are also libraries like PyTest and Nose. I haven't used either of those. And there's also a library called Coverage that helps you estimate your code coverage in Python. I have not used that personally either. And then there are a couple of related concepts that are worth discussing. There's this idea of TDD, or test-driven development. The idea with TDD is essentially that as opposed to writing code first and then kind of building, you know, writing a test to test that code after the fact, you write your test first, you run your test and see that it fails, and then you write your code, you basically fix your test and then keep running it to see if it passes. In the case study, for example, where using, again, a unit test to test that a log file will is actually created. So before you actually start implementing your logger library, you write a test that, calls a function, and you kind of assert, and we'll see this when we dig into this in more detail, but you use this kind of assert concept that says this test passes if the file actually exists. And then, you haven't implemented yet, so the file doesn't exist, or probably you don't even have the function, so the whole thing blows up. So then you go put in the function, you go implement your logging, you run it again, and you see that it passes. And so now you know that, your function does what you're expecting it to do. And so TDD is kind of, building the whole idea of testing into a kind of a broad philosophy. My sense is that, it kind of blew up in popularity around the time of kind of agile methodologies. When would this be, like early 2000s, maybe 2003, 2005, that kind of thing. My sense is that it's less religiously adhered to now, though still an important concept. And then there's CI/CD. CI is continuous integration. It's the idea of merging developers' changes frequently into a common source code repository. And this is in contrast to, if you think about a big software project that, where you're kind of doing traditional waterfall development. You've got developers that are running off to implement features. They, might take a month to implement a feature and then try to, merge it back into the kind of the source repository and the master system. And, what they've done is diverged so far from what everyone else has done that it takes weeks to, integrate things back in. In a CI/CD world, the idea is that you've got a test suite that runs typically automatically. And when a developer commits a change for the feature that they're working on, which should be done relatively frequently, like daily, that test suite runs automatically, either on commit or at the end of the day, depending on how long the test suite takes to run. And the result of that test suite is reported out to everyone. So, if a developer checks something in that quote unquote breaks the build, then, they potentially everyone else is, alerted, and, that needs to be fixed immediately. So that's the idea of continuous integration, and it keeps you from having to have these kind of long cycles where you're trying to integrate in new code after you've committed it. And that's usually paired with CD. CD can stand for continuous delivery or continuous deployment. Continuous delivery is the idea that kind of similar to CI, you're iterating on your software in short cycles, but with CD, the idea is that you're deploying it out to production in short cycles as well. So not just integrating it into your source code repository, but that source code repository that then gets deployed relatively frequently. The course makes the distinction between continuous delivery and continuous deployment, where continuous delivery is you are manually deploying your software frequently, and continuous deployment is you've got kind of an automated pipeline that, so someone checks in code. This is the CI part. Someone checks in their code. A set of a test suite is run. If the test passes, then that code is automatically checked out to the production website. That will be a continuous CI/CD in the automated sense pipeline. I think in reality, kind of the CD is part of this. I think people use delivery and deployment relatively interchangeably, and don't necessarily always mean manual when they say delivery, and always mean automated when they use deployment. But strictly speaking, that's the distinction. I think that's it for testing. Any questions on testing?
Yes, so Sam, one question here. When we are doing this testing, we can't actually test the results. Like in a traditional software development, what we do is that we compare between the expected output and the actual output, and we can test that way. Say there's a test case, and we know that this is going to be the expected output, so we test that way. So in a AI or ML kind of software, we can't do that kind of testing. We can do only that sort of testing you mentioned, like whether the data type we are passing is correct or not, what is the format is correct or not.
Yeah.
That's the only thing we can do.
Yeah, so that is largely true, although when we talk about the performance drift, there are some things that we can do to alert ourselves to when our model isn't behaving the way we expect it to behave from like a statistical perspective. But here we're largely talking about the kind of traditional, software things that you mentioned, like, types and, returns and files created and that kind of stuff.
Right, got it.
Any other questions on testing? All right, cool. Actually, quick detour to logging before we get to the performance drift piece. So, in order to evaluate our model's behavior, kind of after the fact, once they're in production, we need to log the various aspects about the model's behavior and what the model is doing. And we are given a set of kind of minimal features that we want to log, or things that we want to log, and optional things that we want to log. In terms of the minimal or kind of required, logging things for machine learning models, we should be logging the amount of time it takes to process a request, because it directly affects the end user's experience, and can be something that, maybe your model, it has a very quick inference for most data, but some data causes it to take much longer to inference, weird things like that. So we want to model our models, we want to log, our models runtime, so that we can kind of report and generally monitor that. Timestamps are used to evaluate the system's performance under load and kind of relative to concurrency. So if you've got a log file, this is something like doing a histogram or something like that, or that shows you, or a chart that shows you the number of requests per second that your model is handling. And this also will be useful in looking at events that affect the relationship between performance and business metrics. What they mean here is, if a user, if something happened, yesterday at 2 o'clock that, is not, wasn't good for the business, or that you need to investigate, well, having those timestamps in your logs would be a good thing. So kind of no big surprise there. When you're building inference, for inference, predictions are, the output of your inference, and you want to track those predictions. In the case of in case of a classifier, for example, if the classifier is returning all of your classes and the probabilities of those classes, you want to log those as opposed to just the highest probability thing. So you have a little bit more information when you're trying to debug things. It's also useful to have the input data itself, of course. In many cases, the input data is too big. For example, if you've got an image detection model, you don't want to necessarily stuff images into your log, but summarizing information about the input can be very helpful, such as the shape of the input, so that you can kind of debug issues that come into play when your model isn't receiving the type of information that it expects. And then, finally, a version number of your model, ideally tied into some kind of automation, like if you're checking your model and if you're using Docker to containerize your model, then maybe a Docker SHA, or if you're checking your model into Git, then a Git SHA, some kind of automated model version that doesn't depend on human tagging, is ideally kept in your log files. And then there's optional logging features like tracking request IDs. So if you're, if each request has an ID, and you're, ideally kind of tracking that all throughout your application. So, maybe when it hits your load balancer, you're generating the request ID, and then when it hits your web front end, that's being passed, and you're logging it kind of at the Flask level when it's serving a request, and then when you're making an inference, you're logging that same request ID there. That will allow you to trace errors kind of end to end through the end user experience, or correlate issues, which is why these request IDs are often called correlation IDs. We talked about kind of the saving the input data, your feature data shape. If your feature data is small enough, you can just save it all. In the examples, we work with the Iris database or data set, and the features in that case are just 4 numbers related to the petal width and length and stuff like that. And so you can just send all of that into your log because it's only 4 numbers. Likewise, you can do, that's at inference time, you can do something similar at training to make it easier to debug problems with training. If you are doing end-to-end testing, you can capture other attributes of your requests. If it's if the request comes from the web or mobile, if the request, if the log is being captured at your web app tier, or at your prediction tier, if you're doing some kind of unified log, you'll need to be able to differentiate those types of requests. In the solutions to the case study, they also capture notes about the model version. So anything else that you might want to use that is, not going to make your logs file size explode, but that would be helpful in testing, you can add as part of an optional logging field. And then finally, probability. So if you're making a prediction, the probabilities of your prediction can also be helpful. So in implementing logging, there are lots of ways to do this. In the case study, for simplicity's sake, we just use CSV files. Those don't scale very well, but they work for the sake of what we're doing. Python has a legit logging module. There are also more kind of scalable enterprise-grade approaches like Elasticsearch. Elasticsearch is an open source kind of logging and search index system. It's often used as part of, or referred to as part of, what's called an ELK stack. ELK stands for Elasticsearch, Logstash, and Kibana. And together these will allow you to kind of grab logs from a variety of places, index them so you can more easily search them. And I forget what Kibana does, actually. Maybe visualize them in some kind of way or do analysis. And then Apache Commons logging, I haven't looked at in more detail, but I'm assuming that's one of the many ways that you might, or I've seen it come up in the context of like logging, from websites out to HDFS, or Hadoop type systems. But I'm imagining that it supports a variety of deployment scenarios. Question here in the chat: Can we Docker our model directly from TensorFlow serving? I heard that TensorFlow serving can replace Flask, but haven't used that tool yet. There are a bunch of kind of inference tools that you can use. Flask is just a simple example that we use in the course. I think last time we talked about Bento, which I've heard good things about. But there are also there's also TF serving and many others, and you can typically containerize those. So performance drift. So there are a bunch of different types of performance drift. The main idea is that your model, performs when you first put it into production, and over time stops performing or stops performing as well. Concept drift is the subset of performance drift that relates to statistical shifts in distribution. So your predictions are changing in distribution over time. That is often related to either sampling or selection bias. Sampling bias is you built your model on kind of a non-representative subset of the population than what is seen in reality. So in the case of an object detector, you've trained your model on, an imbalanced data set that has a ton of cats. And when you put your model out into production, you see equal proportions of cats and dogs. And so, so your model is not going to perform as well because it doesn't represent what's out there in the world. Selection bias is, very similar, but maybe you trained your model on, balanced classes of cats and dogs, but what the model sees in the real world is, dogs get way more popular. And so the real world data is an unbalanced data set. In any case, those can result in concept drift, or the distribution of your test data, the data that your model is seeing, rather, being different from the data that it was trained on, and thus your model failing to perform. There are other types of performance drift, or things that will cause your model not to perform. One is if the software just breaks. So for example, if you built your model on one version of a framework, and then you change the version of the framework that your deployed model depends on, and it does things slightly differently internally, that could cause your model's decisions to shift. Data changes are another one where either the semantics or distribution of a feature change. If the distribution of the feature changes, often that might be more related to sampling or selection bias, but an example of the semantics of a feature change might be, let's say your predictor is, built, you're doing object detection again, and your predictor is, expecting single channel images, and a developer working on another part of the system decides to send in color images, 3-channel images. That might cause your predictor to blow up, or cause unexpected behavior. And this kind of thing happens all the time when you've got separation between the folks that are building and deploying models and the folks that are using them via other apps, other parts of the system. Maybe you're there's a feature that you need to make a decision that just disappears and isn't computed anymore, or it was a string and now it's a number, or vice versa. And this is where, this is a particularly useful area to have unit testing around, so that it's a lot harder to find this stuff when it's in production than if you are, running a unit test and that flags a change. And so, talking about concept drift, this is the idea of, I've got a model in production. The data that my model sees is, shifting from my training data. How do I do that? And Wen was asking in Slack a similar question. I've got a model in production, and how do I know the accuracy of my model when it is, I can calculate the accuracy of my model in training, and I can calculate the accuracy of my model in test when I'm testing it against labeled data. But in the real world, when I've got this model in production, how can I test the accuracy of the model so that I know when it's decreased? And the reality is, if you're, to compare accuracy, you may need to go out and, capture some of the data that your model is seeing and label it. And then you can calculate the accuracy of the model. But if you want to, look at performance and don't necessarily need accuracy, there are other things that you can do. One of which is look at the user's behaviors that result in that your model results in. So, for example, if you are if you've got a recommendation system and you predict that a user has a propensity to click on a link of X, and over a period of time the users don't click on the link that you're expecting, at the frequency that you're expecting, then you know that something's going on with your model, and so you can kind of log the behaviors that the users are taking and use that to determine if you need to take action or if your model is underperforming. Similarly, if your model is trying to detect fraud, you can look at whether fraud actually occurred. That will, at some point, maybe it's not immediate, but at some point in your, kind of downstream, in your business, someone's going to run into the fraud and, we'll make note of it. And then you can use that to kind of calculate your accuracy. That's more of an example of implicit feedback. In other cases, you might ask the user, you see this, on, systems like Facebook. Facebook will, you upload pictures and it will try to match the faces in the pictures with a person. I don't know if it still does this, but it used to say, hey, is this Joe? So you're asking the user for explicit feedback, and you can use that to tweak your model. And then, of course, you can, again, kind of always go back and collect data and label it, and then use that to check your model performance. And so what about with classification problems? Well, the object detection is an example of a classification problem where, maybe you're predicting, that an image has a cat. You could ask the user, hey, did this image have a cat in it? And based on their input, you can kind of tune your classifier, or you can take the images that the users have submitted and label them. I've also seen there's also kind of a research topic. There are kind of research-based approaches for trying to estimate classifier accuracy on unseen data as well that you can look into. But the main things that the course talk about for performance drift are, one, for detecting concept drift is using outlier and novelty detection, which came up earlier in the course. Earlier in the sequence, I forget the specific course. Recall that outliers and novelties are similar. The main distinction being whether we, expect them or not. So, if in our training data set, we kind of define that, data outside of a certain set of bounds are not expected, then, when we're looking for data outside of those bounds, we're looking for outliers. If we don't have that kind of explicit definition of, or expectation of outliers in our training data, then that's called novelty detection. And we're, just looking for data that statistically isn't like the other data that we've seen before. And in the absence of labeled data in a prediction scenario, we can use this novelty detection idea to say, hey, is the data that we're seeing, statistically similar to our training data, or would it represent a novelty relative to our training data? And use that to trigger, either a retrain or investigation or one of the feedback loops that we've discussed. We also talk about, explore kind of these different distance metrics as a way to characterize shifts in the input features. And we'll talk more about that or look into that more deeply when we go into the demo, which I think we're ready to do that now. Yeah. All right, so one of the first demo in this module is around drift detection. So before we do that, so you have to manually label the ground truth for everything. Can we take a sample data instead? Sure, you don't. If you've got a model in production, you can periodically capture a sample and have that labeled and use that to see how if your model, what your model accuracy is during that sample, but you have to be careful that your sample is representative. So you wouldn't want to take your sample during, if you're a retail site, most of your customers are, in America, you wouldn't want to take a sample of data that, is at 2 o'clock in the morning because the buying behaviors might change, or right after you run a promotion because they'll be influenced by the promotion, or during your high season. You'll need to be strategic about how you capture that data, that sample. So this demo goes through drift detection. We review kind of the outlier and novelty thing here and some of the ways that we see performance drift that we've talked about. And so we'll just go through the various functions in this model, and we see these later in the case study. There is a train function that takes in some training data and some labels and model name and or a saved model. Let's see. And basically, does a test train split, fits a model, SVM, with some given parameters, and then runs a predict on the test set and prints out a classification report, and then saves the model. There's a weird line in here that it was not obvious to me what they're trying to do here, but first they fit their
Sam,
yep.
Are you trying to share your code screen? Because I still have performance drift slide up on this.
Oh, okay. Sorry. Yeah, let me. Thank you, Tracy. All right. So do you see my screen now?
Yep.
All right. So again, I was just going through this train model function. So standard stuff here: test train split, fit the model, given some parameters, do a predict, and print a classification report. That's our train model. They do this weird thing here where they fit the model again on all of the data, not just the test data, and then they save the model that's fit on all of the data. It's not obvious to me why they're doing that and why that's not a really bad thing. Maybe maybe they're training, maybe the assumption is that the training model is being passed only training data, and doing the test train split is really only for the purpose of printing out this classification report on the kind of a subset of the training data. But I thought that was kind of weird. I ran it with and without that, and it didn't seem to make any significant difference in the results. But that's something to keep in mind. And it was also in the case study code. And so you'll want to look at kind of the semantics of how you're using this train function in the code. Are you using sending only training data, or are you sending all your data? In which case you'll have some leakage.
Yeah, my understanding from some other things, and this may be imprecise understanding, is that you definitely want to do your test train, even validation splits while you're developing the model and picking your hyperparameters and that kind of thing. But once you've decided you have the model and you've locked down on this is the model that I want, then you do train it on every bit of label data you have, and that's the thing you deploy into production. So maybe that's the idea behind there. Is that your experience as well, or your understanding from your background?
Yeah, it would. I guess it depends on where. It depends on how the training is, how this train model is being used. If it's being used as part of that experimentation loop, or if it's being used later in the cycle, as you're mentioning. That is the kind of what I was referring to earlier in terms of the semantics of how you're using it. But that is consistent with my understanding as well. So we've got this train model function, and then we've got a predict function, loading our model, starting a timer, loading our model. You're doing some input checks like we've talked about, making sure that the input data is a list, and if it's not a list, reshaping it. Doing the prediction against the model, grabbing the prediction probabilities, and then kind of formatting the runtime and returning, actually calling the logging function and then returning the prediction. So that's predict, and then this is your logging function, given a prediction and prediction probabilities and a query and a runtime, kind of print out a log line in the log file. And again, here for simplicity's sake, they're using CSV writer. And so putting this all together, they're loading the iris data set. This function here, basically what we're trying to do is demonstrate model drift by varying the class balance that our model is exposed to. And the observation is that if we use all of the iris features, the model is so robust that we don't really see a difference. It doesn't matter. And so what they're doing here is they're only using the first two features in the iris data set, the sepal length and sepal width. And so we're throwing away the petal information. And so we are doing some stuff with our log file, training our model, and then running a predict on our predict, and then we're running our predict for just a handful of kind of sample queries. And so this this classification report comes from the training step, and then these predicting comes from our prediction, and these are the values that we predicted for the different queries, 1, 2, and 0, and these are classes within our data set, types of petals or flowers. So next we look at the class distribution, and we see that the 3 classes are evenly distributed. And so now we get into reweighting, like simulating sample shift in the data by reweighting these classes, the result of which is, as opposed to 50 of each class, now we have 38, 38, and 75. And this is for a given weighting of a quarter, half. But we, to kind of simulate drift, we vary that from a third to 33% to 0.92% weighting of class 3, and kind of make some observations based on this. So we see in particular that actually performance doesn't change all that much, because SVMs handle the class imbalance pretty well. But in a sec, we kind of will do some visualization and characterize that a little bit better. So we're using to do the outlier test, we're using elliptic envelope, and to look at the distribution changes, we're using this Wasserstein metric, and then we're for each of the weightings that we're running, so this drifting weights produces the different weightings. And then so for each of those weightings, we're calculating a bunch of metrics. The percent of the class, percent of that third class, the Wasserstein district distance in our input, the Wasserstein distance in our output, the outlier percent in our input, and the outlier percent in our output. For the distance in our input is in a production setting, we won't typically have labeled predictions. So this one, we're only able to calculate because we have we're working on with a fixed data set here, but we can calculate this the distance in the distribution that we trained on and the distribution of our input data, and that's visualized here, and you can see that kind of as the class imbalance, the class gets more skewed, this distance increases. It does also increase in the the target variable as well. The outlier percentage I thought was kind of weird. I would have expected it to be similar, but in fact, it kind of peaks here, which is actually when our performance is lowest, but otherwise the range is not that big. They mentioned that we might set a threshold of 5% on this outlier percentage, but it doesn't ever get to that. So I'm not, that was kind of confusing for me. I don't know if anyone has any thoughts on that particular point.
This whole slide, I didn't understand what they were trying to do with it. So I was looking forward to your explanation.
Yeah, so the fortunately these are all kind of out of the box metrics that we're able to use in scikit-learn. So for each of these for each of the kind of test cases that we're looking at, a test case in this case being shifting the distribution of the shifting the class distribution in our let's see. So yeah, we're shifting the distribution in the data that the model is seeing in production, like at inference time, as opposed to training, and trying to get a sense for how does it impact our score? And again, the answer is not necessarily all that much, or at least it doesn't tank the score. But then we also want to ask the question, well, how might we detect this kind of shift in production, or this kind of shift in our distribution in production? And we use a couple of different metrics for that. One is this Wasserstein distance, and the other is the outlier percentage. The Wasserstein distance is looking at let's talk about the outlier because that's a little simpler. It's saying for this this input data point that that we're given, that would be that's the outlier percent here. All right, so let's take a step back and go to this, go through this code. So this is a classifier. So we're basically just initializing classifiers on our input and output. And here we're fitting on, we're fitting them with the appropriate data set. And then we are doing this kind of drifting where for each of the these different weights that we've calculated previously, we are coming up with X new and Y new, which that's back from the simulate samples. So we're coming up with a distribution of samples from that of that weight distribution.
I think I figured out where some of my confusion was coming from. I somehow was thinking, because I live in the world of binary classification so much, that I was looking at the 50% thing and just now realized, wait a second, no, if this is a 3-class thing, then if you have balanced classes, you're starting down at the 33%. So that was I was a little bit confused by the ramping up when I expected it to be, you know, a different shape. That's because I
Got it.
was thinking 50%, not 33%.
Yeah, this is, there are 3 classes here, and there are 150 data points. And so, you know, here when we count, before we do the reshuffling, we've got 50 of each class, so it's 33%. And then down here, you know, after we shuffle, these are the, again, absolute counts, and they represent 25, 25, 50% of our classes. And then, so we're, so we kind of reshuffle our data here. The, let me just make sure we're talking about the same X and Y. I think we're talking about just our, you know, our full data set. And then we actually measure the number of labels of class 3, and that and then divide by the total number in the data set, and that's our class 3%. Here we're calling this Wasserstein distance on the it's calculating a distance between the distribution of our X, our data set before we shuffle it, and the shuffled data set. And this is calculating the distance between our labels and the labels after the shuffle. The after the shuffle inputs and outputs are analogous to, you know, what we might have captured from a production environment. And then we're predicting on the shuffled data. So we're running our classifier on the shuffled inputs, and then this one is fitting a classifier. The classifier is our elliptic envelope. So we're trying to detect outliers on our new shuffled data set and our new shuffled set of labels. And we're doing that for each of these drifting weights, and then kind of visualizing it. So again, kind of as we increase the percent of our class 3 from, you know, equally weighted to, you know, very dominant, the distance between our you know, equally weighted, you know, data set and our kind of shuffled or reweighted data set becomes greater statistically, and that's reflected in this Wasserstein distance. And then we're also detecting outliers in the input, and they remain relatively small. This one, again, I'm a little, I would have expected that this is also kind of correlated with the degree of imbalance.
Yeah, that does look weird.
Well, let's see. So maybe not. So the outlier detection is based on it's based only on the reshuffle data. So if your reshuffle data is very skewed towards class 3, then maybe most of your data points are in class 3, and so you don't have a lot of outliers, whereas if it's more equal, then yeah, I don't know. I need to dig into that a little bit more. I think it's something along those lines. When your data set is highly skewed, your class 1s and class 2s aren't as prevalent, so you have fewer outliers. But that is something I'll need to dig into some more. So going back to, so any questions on this? We spent a lot of time, a lot more time on it than I expected. But the basic takeaway is that when you've got models in production, you're going to want to use tools like these distance metrics and outlier or novelty prediction to determine whether the data that your production model is seeing is, similar or different from the data that it saw in training, and then set thresholds to alert you if it is in fact different. And then as a final point, if you've got very highly dimensional data, it can be helpful to do dimensionality reduction before trying to do outlier detection or calculating this distribution shift. Any more questions on this? Ask a silly question. Does sklearn library work well for a big data set? I guess it depends on your definition of big, but it can work well for pretty large data sets. Of course, you'll spend a lot of time in training. All right, so then a last bit of coverage was on securing machine learning models and talking about adversarial threats. A couple different kinds of adversarial threats. One is poisoning attacks, where your adversary is injecting malicious data into the training set to try to corrupt the model. A great example for this, for me, is reCAPTCHA. reCAPTCHAs annoy the hell out of me. I feel like I'm an unpaid laborer training somebody else's classifier. And so oftentimes, if I've got time on my hands and someone is, has a reCAPTCHA that's asking me to pick out the chimneys, in fact, this happened just yesterday, I will just pick everything or pick, random things just to kind of mess with it.
That is too funny. You're evil.
That is an example of a poisoning attack. And evasion attack is when the attacker is trying to exploit particular aspects or blind spots of your model at inference time to try to get the kind of results that they want. There are different ways to defend against these kinds of attacks. You can do stuff with your inputs to try to minimize any to kind of minimize the effect of perturbations in them. So one of the big areas that of interest around adversarial threats is in image detection or object detection. Think of the scenario of a self-driving car. It's got a camera looking on the road. There have been these toy examples where you can add some stickers to a stop sign and have an object detector recognize the stop sign as a some other road sign or a some other object. And so these kinds of attacks work by injecting noise into the inputs. And so by pre-processing those inputs, for example, smoothing, you can kind of get rid of the perturbations or minimize the effect of the perturbations and decrease your model's sensitivity to them. You could also actually take those adversarial examples, the perturbed examples, and put them back into your training set with the correct labels. You can try to detect attempts to attack your model at runtime and flag those inputs and act accordingly. Really interesting, fields right now, and I thought I wasn't aware of this NIST report, National Institute of Science and Technology, on the a taxonomy and terminology of adversarial machine learning. You can take a look at that. There is an interesting demo on the, IBM has this toolkit called adversarial, what is it called? Adversarial Robustness Toolkit. And they've got some demos online. So here's one where we've got an image of a cat. It's a Siamese cat. Our model can predict with 92% probability that this is a Siamese cat, excuse me. And then we can apply these different types of attacks, say a fast gradient attack. We can set the strength of that attack, and we can get the model to predict different things. So here we've gotten our model by adjusting the strength of this attack to predict different types of cats, an Egyptian cat in particular. You can try another attack. Now with a low strength C and W attack. I forget what C and W is. But now we can get our model to predict that this thing is an ambulance. And we've also got the ability to see if we can detect any kind of perturbations in our input image. Oops. Why isn't that working? So let's see if we make this high. We still can't really, it's imperceptible noise that we're injecting into our image, but now our model is pretty darn sure that it is seeing an ambulance. Some of these other methods change the input image more perceptibly. Like this fast gradient method, when we set it to high, you can kind of see that something's going on with the image. It almost looks like an artistic style transfer, and it's, maybe this is like an adversarial art form. Adversarial robustness toolkit. There's some kind of punished thing in there. But so we've got all these different types of noise that we can try to apply. Again, this is my favorite. The cat now is definitely an ambulance. And then there are these different defenses that we can play around with. So what we're doing here is we're injecting noise into our image. Feature squeezing is trying to smooth out the noise that's being injected. And so now we're able to decrease the input of our, decrease the effect of the noise that was injected. And we can see when we look at the result of the feature squeezing, we've we've kind of manipulated our image rather strongly, but we not so much that the object detector can't detect what it actually is. In fact, we have we're back up to 94% certainty that this is a Siamese cat. So this is something that you can play around with. There's also, you can also look at the code behind this. All right, Jose, thanks for joining. Jose's got to run.
Sounds good. Thanks, Sam. Sorry, I got to run, guys. Take care, everyone.
Yep, take care. So, all right, so that brings us to the case study, which, as I mentioned in the beginning, I'm still working my way through this one. This was a pretty tough one for kind of a variety of, infrastructural types of reasons. But the basic idea here, I think, is actually a really interesting one. It's like we've gone through this course, we've learned how to build these models and how to build inference and how to log them now and how to encapsulate them into Docker containers. Yeah, I think the goal of this case study, and what makes it worth investing the time in is that, they're trying to have you build up a framework that you've built so you understand how it works, that you can apply to, any future model that you create. So, we're kind of leaning on some of the earlier lessons about kind of encapsulating your code in standalone modules and making it robust, and we're pulling that all together into again, a framework that we're creating that is modular enough that we can swap out the model. And and in fact, we do this in the case study. We start out doing this with the iris data set, and then at the end we swap it out with the avail data set. Different model, but everything in the framework stays the same. And Tracy, in theory, you could swap this out for a melanoma model. And the framework is the same, and you use the same mechanics to deploy this out to a web, microservice that some front end, app could use to do inference against. So I think it's a really cool case study. The first part of the case study is to write some unit tests. So we start out with actually no logger_test.py file and no logger.py file. And the instruction you're given is to, based on, what you see in model.py and model test.py as an example, which are basically the things that we saw, in this drift detection case study. It's kind of based on that pattern, create your own logging infrastructure. And so you've got, oops, that's an old copy. Move some stuff around. You've got this model tests. It's running some unit tests, using a unit test framework against the model. You've got the model file itself, and you want to do the same thing for logging. So the first thing that I ran into here was that couldn't find the logger. And even the solutions did not work. It's like Python model import path issues. So I had to move all my source code under a source folder, create a init.py under the source folder, and import it, change the way it imports both for the model tests and these logger tests, so that it could find my logger module and import these functions. But then once I did that, everything was pretty straightforward. I started with the first test they want you to do is to make sure that when you run an inference, you're creating a log entry. So I started by kind of, actually I wrote the function first based on the model function, creating a log file name. This evolved originally, it was pretty simple. And then kind of writing out a log line. And then so, in the test function, create the log function name, call inference with some, dummy data. And then, in this unit test framework, you're doing these assert trues. There are a bunch of things that you can assert. You can assert that, something is true. You can assert that a set is equal to something. You can assert that a tuple is equal to something. You can, you can assert something is, you can assert something conforms to a regular expression, not equal, blah, 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 blah. So there's all these things that you can kind of assert. And you basically want to, in this case, assert that your file exists. So you start, empty file, you add this, you run it, it fails because you haven't created your log file yet. You create your logging function, then you run the function again. And I can give an example of that here. So this is me running the unit tests. Oh, I'm in the wrong place. What's happening? So here I'm running the unit tests. They all ran fine, but if, for example, I wasn't writing out this file, my unit test should blow up. Yep, assertion. Whoop. I don't know why the existence of the file test did not blow up. So that's one of the interesting things about this. Like you start, my first example of this, let's make sure I save that. First example of that didn't remove the log file. This one should, so that should have blown up. But it didn't. Maybe I hadn't saved it.
Hey Sam, it's Subhashish here. I need to run.
Yep.
So I'll observe the rest of the session. You are going to upload this recording in the site, right?
Yeah, I'm gonna upload this. I actually will probably let's see, what time is it here? I did not complete this, so what I will probably do is we'll either cover it next time, or I'll do a separate video, kind of walk through the project and upload that and point you to it.
Okay, that's great. Okay, thanks, Sam.
Yep. Yeah, so I, as I mentioned, I got as far as, getting the test suite to work. And the next step is to deploy add logging to the Docker container. You know, I started by just trying to get the Docker container to deploy, and I'm having similar kinds of issues with like paths and stupid stuff that I need to work through. So I haven't gotten very far on this. I'm planning to continue to play with it. And depending on the, you know, how much material we have for next time, I will either, you know, like I said, I can run through this case study at the beginning of next time, or, you know, do a separate video that I point folks to.
This gives us, the rest of us, a chance to catch up as well, really.
Yeah. Does that sound like a plan?
Sounds good to me.
All right. Any questions on what we have covered so far?
Just a comment that as you're going through and running into those problems, if you could kind of post hints up to the Slack channel, so those of us kind of following in your wake can maybe avoid making the same mistakes, or know that we've got to tackle something, that would be really helpful.
I'll do that. Yeah, I may, again, maybe I'll like start fresh and see. I never know with these, like, yeah. Sometimes I wonder if I should just start from like their solution and kind of walk you through their solution, which has everything and it's built out, but it's, you know, theirs is a bit more well thought through and robust, and, you know, maybe it's useful to see something kind of quick and dirty, because that's the first step anyway.
Well, it'd be interesting to see how, you know, they solve that logging. You know, if you couldn't find the import, then what does their solution? How did their solution?
Well, their solution didn't work either.
Ah, great.
Yeah, I don't know. They maybe expect you to have a different directory structure or something like that, but I couldn't get the solution to work either. So
Very, very frustrating.
To run their solution, I had to make the same change that I made in mine. I imagine it's probably something stupid. Some, you know, they have something in their path, or I'm using PyEnv and they're not using PyEnv, and PyEnv has some, you know, some assumptions that it's making about where things are, you know, that kind of stuff is what takes the most time with all this kind of thing. Especially folks like me, that I'm not writing Python code every day, you know, so I don't have all this stuff in kind of active memory. I have to go search for it, you know, when I run into it, which takes a while.
Well, it should be fun when we get to that. It's nice to have a heads up to realize this isn't going to be just a quick little, oh yeah, I'll just carve out 2 hours tonight and just crank that out.
Yeah. It may be for you.
Yeah, no, I don't think so. All right,
cool.
Thanks very, very much, as always.
Absolutely. Have a great rest of the weekend, and carve out some time to work on this case study.
Yeah, definitely going to do that. Actually, after I finish the case study from last week, then I will carve out time to work on this.
Nice. And did we go through that in its entirety? I think we did.
I had to bog out a little early last week, so I think you seem to be pretty far along, but I assume you finished it. But
yeah, if you have any questions, reach out in Slack.
Yeah, I'm still trying to perfect my Docker. I actually bought a book on Docker as well as that video, so I'm starting to feel more comfortable with it. But as I say, ran into the GUIs on Docker. I wonder. So if I succeed in that, just, you know, I'm kind of like you. Once I get the bit between my teeth, it's kind of hard to let it go.
Yeah.
So if I succeed at that, I'll just kind of share as a side thing. Oh yeah, you couldn't use the Alpine, you had to use the Ubuntu base, et cetera, et cetera, et cetera. So yeah, but we'll see. Given that it is graphic card dependent, it will be interesting to
Yeah, I would
See if
think
that's
for
even
that
possible.
you'd need to you need to be running like X windows or something to get the thing that's running in your container to talk to your outside of your container window environment. It sounds like a mess.
Yeah, that sounds like what I saw on, like I say, the Firefox. So somebody had a recipe up there for getting Firefox to work, and they had a whole bunch of X window arguments at the end of their
Oh,
run command.
oh,
So
yeah. Yeah, I would go down the Flask web app rabbit hole, especially given the way you've described at least the initial phase of the project. It sounds relatively straightforward.
yeah,
Yeah,
the
you don't
trickiest
have
part
to
on that.
you don't have to worry about the distribution problem of like getting this zip file thing installed on a bunch of people's machines.
Yeah, the biggest hurdle with that is all the internal security stuff. Where, as I mentioned in a side chat with Jose, they kind of not real big on people just spinning up web servers internally.
Uh,
So, but there are ways around these things. So, yeah, we have a whole internal group that, like, I mean, in theory, I shouldn't even be installing my dev tools on my box because they haven't been vetted.
yeah.
Because as you can imagine, hospitals are pretty dang worried about malware getting in and locking everything up. So, um,
Uh,
so the idea of even deploying an app that I wrote myself, they're like, well, we have to run it through our security audit,
right.
and we have to, so
Interesting.
that's not consistent with we need this next week.
Well, you could actually. I wonder if distributing a Flask app as a Docker container that people run locally maybe a way to do it.
Yeah, yeah.
If
Well,
the issue is spinning up a web app that like maybe they're blocking different ports or whatever. I don't know.
yeah, I think what I'm going to do is as a parallel approach where I'm going to finish the app as just the native GUI thing. And that way I can also get feedback. Like the 2 times I've already put it before dermatologists, I've gotten some pretty good feedback like, could you do this instead, or this would be more helpful. So kind of refine it quickly with the client version. And then once we've got something stable, that's where in parallel, I can be spinning myself up on Docker or Django or whatever. And I mean, Flask or Django. And then, because Flask seems to be really more geared towards microservices and stuff, whereas Django is more towards a full web app thing. Is that a crude, accurate assessment?
I would say that that it's crude and not inaccurate. Or inaccurate? It's not inaccurate, but it's.
I didn't fail to disprove the null hypothesis.
So Flask is, I think the difference is that Django is really designed for content management systems, right? Django was created by some dudes that worked at a small newspaper in Kansas. And so it's really big on creating content management systems. And it's relatively heavyweight. Flask, on the other hand, is basically, only one step removed from a Python web server, right? It spins up a web server, you define some function, you basically, Flask in its essence is allowing you to route web endpoints like /predict to functions in a Python file. That's all it's trying to do.
Yeah.
And deal with HTTP. And so unless you're trying to, you can build like full web apps with Flask. If you're trying to build, a content-based website with lots of pages and posts or other content types, then Django might give you a head start. but I guess that, I'm trying to dissuade you from getting overly caught up on kind of microservices as a, specific thing. It's not necessarily for microservices per se. It's just for like, simple web apps that have a few routes and, a few kind of, core functions.
Well, 95% of this thing is actually just GUI, right? So
Mm.
the biggest thing is how am I going to, what toolkit am I going to use to construct the page? Am I going to, go down the road of jQuery, or, is there a better sort of, hey, if you're coming from the Python world, it'd be better to actually look at this library. So that's kind of the parallel investigation I guess I need to figure out.
Yeah, good questions. One is asking, can we use Node.js to build ML model APIs? I don't see why not. I know there's like TensorFlow JS. As long as you have a model in JavaScript, you can use Node to serve it up. And there are at least a few JavaScript machine learning APIs, frameworks, TensorFlow JS being one. All right, cool.
All right, see you next week.
Catch y'all next